So today we have, it's one presentation, but presented by two of our CCOM members. We have first up Avery Muñoz, research project engineer at the center with the ASV lab. He holds a bachelor's in computer science from Wentworth Institute of Technology with a background in robotics, custom automations, and AUVs. At UNH, Avery works as an engineer on the Autonomous Surface Vehicle project, developing control systems and tools to assist research, as well as all the DriX stuff also. As to Val, as you all know Val Schmidt, but he leads the center's marine robotics program, where he and a team of engineers, including Avery, and graduate students solve problems to make autonomy practical. How much of this do you want?
That's fine. That's perfect.
Okay. Please welcome our speakers. Thank you very much.
Yeah, so I'll introduce what we're talking about a little bit and then get into my presentation. So we're going to give you guys a little bit of a higher level overview of some of the work that we did last year. It's kind of occurred to us that some of the stuff sometimes doesn't make it back to CCOM, and we did some pretty interesting operations last year. So we're going to talk with you guys a little bit about an operation we undertook over the summer in American Samoa, and then Val's going to talk as well about the dual-DriX project, which we undertook, which is out in the Gulf of Maine, and took place a little bit closer to home. We had some operations here at CCOM. So it's going to be less of a technical overview. I'm going to talk a little bit about some of the smaller projects that we undertook and kind of the change in mindset, but it's going to be more concept of operations and operational research stuff. So I'm going to get right into it. I'm going to give you guys a little bit of an overview on an operation that we undertook in American Samoa in August of 2024. So this operation was focused on Vaiaulu, which is a seamount to the west of American Samoa. And I'm going to give you guys a little bit of an idea of how we changed our concept of operations and really how we changed our mindset as ASV pilots. I don't think I have to give too much background for what CCOM is, but just to familiarize a little bit with the ASV lab in particular, we do a lot of research focused on the integration of autonomous surface vehicles into seafloor mapping, into other science support work as well. And we've worked a lot with Ben, that yellow boat you may see in the high bay pretty often, as well as DriX, which is a vehicle from a company in France called Exail that I'm going to focus on pretty closely today. The operation that we underwent was in 2024, but just to give a little bit of context, I have some pictures from some of the integration work that we did aboard the Nautilus. And this red boat right here is the Exail DriX. This is hull number 8. That's owned and operated by the Ocean Exploration Cooperative Institute and maintained and operated pretty closely by the ASV lab. Larry's shaking his head at me. It's operated pretty closely by the ASV lab here at CCOM.
Owned by us now.
It's owned by us. All right, there we go. And we did a lot of work integrating this DriX 8 vehicle into the Nautilus for ship-based deployments. So traditionally, a lot of the work that we've done with ASVs has been really line-of-sight focused. We've been pretty heavily dependent on Wi-Fi, on marine broadband radio, which gives us a maximum of maybe 20 kilometers of range. So a lot of the work and the research that we were doing traditionally was focusing on taking an ASV out on a large ship or taking it to a shore-based deployment station and then operating it pretty close to that deployment location. And a lot of the work that we've done in the past year has been changing that concept of operations to what you're going to hear me refer to as OTH, or over the horizon. And when I say OTH, really what I'm talking about is we're transiting beyond that traditional line of sight communication range. And a lot of that work has been pretty heavily dependent on things like the Starlink, some of the more advanced iridium systems that we've been using to kind of push our vehicle further and further. 2023, DriX 8 underwent a refit. The big focus of this was actually the integration of an EM712. We were the first customer vehicle to actually get this sonar, this deeper water sonar integrated onto a DriX vehicle. And it was really exciting, but one of the other things that we underwent during this refit was we actually had Starlink integrated on board as well. We had a little mast mounted to the back of the DriX with a dish, the high performance Gen 1 dish mounted, and we were getting pretty good performance. You can see this is actually a video the first time the DriX 8 was transited out of the harbor in Honolulu, where we underwent the refit. And we actually were piloted out of the harbor over our new satellite telemetry system with an escort, of course. But this was kind of the first time that we actually pushed the vehicle out into the ocean and were able to test it. It was pretty exciting. And 2023, we also underwent some more ship-based deployments. And this is an entry that Larry made in our operational log, which was really exciting. This was kind of the first time, we were still operating off the Nautilus at this time, but we actually were able to push the DriX beyond that traditional line of sight telemetry range. And we had the Nautilus mapping in deeper water about 30 kilometers away from the DriX, which was up working with the Mesobot system, doing some verified directed sampling, as well as some shallower water mapping with that 712. So this was really exciting, and this operation in 2023 was really eye-opening to what 2024 was going to be focused on with these vehicles and how our operations are really going to change. And we were really going to be focused on kind of this multimodal operation where we could have pilots who are on board a ship nearby deploying the vehicle. We could have pilots here up in New Hampshire. We could have pilots actually in France working with the vehicle, operating and piloting, taking watch rotations. And that has changed the way that we've had to think about the staffing of these operations and the way that we actually design the operations pretty incredibly. So it's been really interesting. We spent a lot of time in 2023 and early in 2024 focusing on what was going to change from a safety perspective with the vehicles when we started operating over the horizon. It's honestly, from a technical perspective, somewhat easy to put something like a Starlink dish on one of these boats and then start driving offshore, and you can get pretty far away. But when something goes wrong, or when something unplanned happens, or you need to make adjustments to your operational mode, it can be pretty dangerous. And we always talk about kind of the core tenet of our operations being safety of the public first, safety of the vessel second, and then safety of the mission and success of the mission. So we really wanted to focus a lot on analyzing what was going to change. You know, the emergency response time for a vehicle that's 100 miles away versus something that's 5 miles offshore is totally different. And the response from a crew vessel could be totally different when you're nearby like that. Your time to maintenance, your ability to refuel is totally different. The transit times that you're going to undertake for that operation will be totally different. One thing that we kind of took for granted is that when we're operating nearby, you can get eyes on the vehicle pretty easily. You know, if you're working off of a crewed ship, you're deploying the DriX and then you're staying nearby, you can always bring the DriX nearby and see if you have a line fouled across the bow or see if there's something stuck on the vehicle. When you're 100 miles away, that's not as possible, and you have to make pretty serious considerations when you change your operation like that. So we were very keen to make sure that we were comfortable with this increased reliance on system stability and the increased reliance on the sensors and diagnostic capabilities of the vehicle, because we want to make sure that we're operating safely, not only for the vehicle and for the success of the mission, but also for the public. So in 2024, finally, I'm going to talk a little bit about some of the work that we did leading up to our big operation in American Samoa. So we did what we call a shakedown cruise out of Honolulu in 2024. This was various fixes that we wanted to make to the vehicle, but also some upgrades that we wanted to make sure that system reliability was really where we wanted it to be, and we were comfortable with the capabilities of the vehicle. So a lot of things like this, for example, are some diagnostic reports that we wrote on data we had collected from the Starlink while testing in 2023. The dish provides an internet connection, and most of the time it works, but when it doesn't work, you really want to know why. And luckily, the dish provides a lot of diagnostic feedback to you. And we spent a lot of time collecting data when the dish wasn't connecting or we were getting intermittent connections and trying to characterize why those were occurring. You know, is it sea state dependent? Do we have bad connectors we need to address? What do the update cycles look like for the dish? We really wanted to understand all of that before it became kind of our primary source of telemetry to go offshore. Another silly thing, like just mechanical upgrades that we made to the vehicle, we outed a bow camera. Previously, there was no real way to see a lot of the actual close area around the vehicle when you were underway. So we have a lot of cameras, like a large camera array on the top of the DriX here that gives us a full 360-degree view around the vehicle. But if you catch a line across the bow, for example, which is actually something that happened in 2023, you could easily wear a hole through the mast like we almost did here, or if you get fishing gear across the bow that fouls the prop, you want to be able to confirm that visually versus just having a dead boat and wondering what happened. So little things like this made a big difference. Adding cameras, this is something that we've talked about, even adding more cameras externally to the vehicle after the experience we had with this one. We also integrated a remote VHF solution in 2024. This was something that was a pretty big prototyping effort for us. We integrated sort of an off-the-shelf device from Garmin, which was previously called Vesper, that actually gave us the ability to make VHF calls to local vessels while we were at sea. So the DriX could transit out to sea, and we could make VHF calls from the DriX on board so that we could call to local vehicles. This is something that was pretty important to us because it's something that could arguably be required for the communication of local vessels, and it's also something that, as we push these vehicles further and further, increases the comfort of the other vehicles operating there, other crewed vessels operating in the area, if we're able to communicate with them. Mechanical upgrades as well. This is a specific one that I featured in this presentation that we had worked with Exail to get implemented, but we had seen things, or actually Exail had seen things like a failing alternator bracket on a couple other DriX vehicles, and we happened to have that same bracket on board. And these are things that we wanted to address because if you all of a sudden are 100 nautical miles offshore, and the alternator belt falls off because the bracket is floppy, you can't just take a crewed boat out and recover the vehicle, or you can't get a maintenance team out there to fix something. It's not like you can quickly make that recovery and make repairs. So things like this really needed to be addressed before we decided to push the vehicle. This is another fun kind of testing operation that we did. We've tested a lot of iridium-based backup tracking devices. So there is a a Sol stop tracker on board, which is a solar-powered iridium tracker that comes with the DriX. But it wasn't quite as configurable or as intuitive as we had wanted, so we spent some time testing a couple other devices. This is actually just like a little hiking iridium emergency device that you can activate and then track for a few days at a time. And we tested more of an enterprise iridium solution as well. And both of them performed great, and it was awesome for these specific cruises to have multiple backups on board in case we were to lose communication to the vehicle. Another thing that changed for us, this gets more into sort of the concept of operations, is we spent a lot of time in 2023 and especially in 2024 as we were doing these testing cruises, collecting a lot of data. We put a larger gondola when we did that EM712 integration, which is larger mass and more drag under the vehicle. And we were really keen to make sure we had a really good understanding of what the efficiency of the vehicle was like. Because if you can imagine you're transiting offshore and you have a set schedule and you have a set efficiency range that you're trying to meet for your operation, but something goes wrong halfway through the operation and the pilot quickly has to make a decision about whether or not they're going to bring the vehicle back to port. You have to have the tools like these, which are some graphs that we generated from some data we collected that give the pilot quick at-a-glance estimates of what the vehicle's capabilities are at certain speeds, at certain RPM. And they're really important because, like I said, you want your pilots to have all the information available to them so they can make those quick informed decisions and then start to tie in more senior, like master qualified operators. But it's important to have these tools available at all your piloting stations. Make sure everyone involved in an operation has a keen understanding of the capabilities of the vehicle when you're going offshore. Another thing we implemented that we tested in 2024 and we used through this operation in August as well as at the operation in October was these real-time endurance estimate models that Val built, where we sort of force our operators to do kind of a watch rotation or an hourly watch checklist. So they have certain things that they go through, the telemetry that they're checking on the boat to make sure that temperatures on board in certain compartments or the water temperatures are what we're expecting. And also to make sure that we're seeing the fuel consumption numbers that we see both at fuel flow into the engine and also the tank measurement numbers that we're seeing, so that we can generate these sort of real-time graphs where you can actually see the endurance of the vehicle get closer and closer to your safety distance. So this is like your turnaround distance at certain speeds. As these numbers get closer and closer, you know, like, oh, as this reaches my safety distance, if I want to transit 8 knots back to port, I now have to turn around. Or I'm only going to be able to go 6 knots now if I want to be able to safely make it back to port within that 15% fuel window that we leave ourselves. So little tools like this prove to be super effective and really useful for pilots to be able to visualize the different tools or the different changes in operation as the operation goes on. Another thing we did was we did a lot of failure scenario planning. I said like 4 times now in the past couple slides that we really want our pilots to be able to make quick decisions and also to have the tools that they need to make safe decisions for the vehicle. So we spent a lot of time going through and creating checklists for different scenarios. If the vehicle dies at sea, if the engine stays on but we lose propulsion, if the battery's cut out and we lose telemetry of the vehicle and we're only on backup, or on positioning backup. Like, we wanted to go through all these failure states and make sure that pilots had at least a couple steps that they could take to start to safely analyze the situation, figure out what the next step should be, and who they should inform. So this was a big push for early 2024 as well, and something that we implemented. And I'll give you guys a little bit of an overview of the operation that we undertook in Samoa. So like I said, this operation that I'm going to be talking about was pretty focused on the operational zone over here in American Samoa, which is about 100 nautical miles, or sorry, in Vaiaulu is the seamount. It's about 100 nautical miles from American Samoa. And we undertook this operation in collaboration with the Nautilus, who was also operating out of American Samoa at the time. But we decided to push this concept of operations to actually deploy the DriX vehicle from the harbor in American Samoa, and then without any direct crewed vessel support, we would transit out to site on Vaiaulu, interact with the Nautilus, work with the other vehicles, the robotic vehicles in the water column, do some deeper water mapping, and then also transit all the way back to shore. So during this operation, just for context, like the Nautilus was operating on site at the same time, and we had provided them with an emergency tow kit, and we had provided them with a remote control, an RC controller, so that they could control the vehicle in an emergency. But we essentially had pretty minimal crewed vessel support. The Nautilus couldn't recover the vehicle on deck in the case of an emergency. All they could do is if we ended up with a dead boat at sea, they could come along and tow the vehicle back to American Samoa for us. So this was a pretty lofty goal for us, and it was going to be the first time that we were really taking DriX 8, pushing it offshore, and making these pretty big changes in our operational design. So just some pictures to show off what the operation looked like. This is our remote operations center that we set up in American Samoa. We were in Pago Pago Harbor. We were actually in a NOAA fisheries kind of tool shack that we had set up. We brought our kind of field kit in to set up our ROC with our backup power and our Starlink for backup internet to make sure that we had our redundant capabilities there. And you can see some nice pictures. Just outside the ROC there, we had a pier set up where we were able to pull DriX into its docking system and also refuel it at the pier there. And we also, this might look familiar, this is the remote operations center just upstairs. We had a team on watch here at UNH as well. Again, one of those big changes that was kind of taking place for us. We were able to leave some of our pilots here and actually put them into the watch rotation and have them help out as well. So that was pretty big. As soon as we arrived, we started battling some pretty serious weather conditions. Hindsight's 2020. The weather in the South Pacific in August is not always the most friendly, and we were seeing some pretty huge, significant wave heights, and the setup coming into the harbor was pretty crazy. And we were also seeing some pretty serious rain, which put a hamper on a lot of our maintenance and a lot of the setup that we were doing. You can see we kind of had to set up a little tent on the docking system so that we could be in the electrical compartment of the DriX while we were improving things on board or fixing things, getting ready to get underway. So there were some pretty significant weather challenges while we were there. So we had to kind of change our operational plan, working with the Nautilus while we were there, to look for these weather windows while we were on site. And I think this was actually on August 17th, we finally got our first weather window to set up out of the harbor and get underway and meet up with the Nautilus. Nautilus had just previously been over to the operational site, or just close over that direction, and they were pretty uncomfortable with the swell out there and trying to get other vehicles off the back deck. So at this point, we decided that Nautilus was going to actually come around to the lee of the harbor here in American Samoa, or of the island in American Samoa, where the seas were a little calmer. And when we transited DriX down around the south part of the island and met up with the Nautilus, we were able to do some engineering dives. You can see some pictures from the interface here. We've got the Mesobot, which is a water column profiling robot, in the water, and the DriX was in AV following mode with Nautilus nearby. So we were able to confirm with the team from Hui managing the Mesobot that all of our communications were working before we got out to Vaiaulu. And this proved pretty successful, but it ultimately wasn't in the operational site we were hoping for. And we continued to see some pretty significant weather issues as we were out here. This is a pretty crazy snapshot from our operator station. This is the horizon, and this is the stabilized forward-looking camera. So when your stabilized forward-looking camera is 45 degrees to the horizon, you're in some pretty serious weather. So coming back into the harbor, we're seeing a pretty severe setup with short period waves as we came into the harbor on shore. It was a little scary, but we made it in. We were able to make some repairs to the vehicle, make sure that everything was ready to go, and then finally, on the 19th, we got another weather window, and we decided that we were going to get underway and actually transit with the Nautilus all the way out to Vaiaulu and attempt some of those verified directed sampling dives, as well as also doing some deeper water mapping. And this, you'll notice it's labeled attempt number 1. This was a pretty harrowing attempt as we got underway. we started getting messages from our Starlink monitoring ROS node that was telling us that there was an update pending for the dish. And at this point, we knew that when you get a firmware update for your Starlink dish, the dish has to reboot. And it turns off completely, and you lose connection to it for a little bit. And at this point, we were approaching this small island, I believe it's called Ofu, that was off the west side of American Samoa. And we figured from the drift model that we were using at the time, we knew that the DriX, when it was not underway, was going to be drifting kind of towards that northwest direction. So we figured we would initiate that Starlink update, lose connection to the vehicle for a little while, let it drift for a little bit while we were in the safer water, and then hope that the connection would be reestablished. Typically, we've seen these dish updates take a couple minutes, and it's usually not a huge deal. As you can see from this map, though, we initialized our Starlink update, and then after waiting about 45 minutes, the Starlink dish never came back online. We never regained that IP connection to the vehicle, which means we were still able to connect over our low bandwidth Iridium connection, but we were seeing pretty degraded situational awareness, and we weren't comfortable continuing all the way out to Waiulu. So at this point, we decided we had a theory that there was 4G connectivity on Ofu. We couldn't figure out if there was actually any permanent residents out there, but we had worked pretty closely with Blue Sky, the 4G provider in the area, and they assured us that there was a chance that we could get a 4G connection. So we used the Iridium system to initialize some go-tos with our automated obstacle avoidance system turned on. We were able to slowly start transiting in towards Ofu here, hoping to get a 4G connection. We actually encountered also some issues with our Iridium link at that time, which we had to address later on in the operation, but luckily, we were able to make it up into Ofu, and we did get a 4G connection. We regained connectivity to the boat. We were able to see our cameras and ensure that all the systems were safe and sound and everything was going well. And interestingly, at this point, we also regained our Starlink connection once we got towards the lee of Ofu and the seas calmed down a little bit, which was something that proved to be a pretty good data point. But we ended up bringing the DriX all the way back to Pago Pago. Out of an abundance of caution, we actually replaced our Starlink dish that was on board with the second one we had been using at the ROC because that one had given us no issues and had already been firmware updated. So we worked with a couple of Starlink engineers, but we weren't comfortable. We wanted to have that other dish on board. And then, attempt number 2, we decided to finally transit all the way back out to Waiulu. And at this point, we were successful making it out to Waiulu. The transit went off without a hitch. We didn't have any firmware updates while we were underway. And we made it all the way out to Waiulu, where we were able to do some mapping of the seamount. We have some kind of beauty shots of the water column here. It was a really, really awesome spot to be able to test out the capabilities of that 712. And then also, like I was saying earlier, the Mesobot, that water column profiling robot out in the water. We were able to use the DriX to do our verified directed sampling, where we actually use our USBL system to give updated positioning to the Mesobot while it's in the water, and we were able to use our single beam EK80 on board to provide some of the scientists directing the Mesobot with information on what the layers look like in the water column. And this ended up being a huge success. This is a slide that we included for the presentation for Exail. Larry was actually also in the Arctic at this time and was able to hop in and actually control the DriX 8 in American Samoa, or just offshore of American Samoa while he was in the Arctic. That was a really exciting step for us because that was it's a good media shot, but it's also awesome and impressive to be able to demonstrate the capabilities of these systems. We were able to put a couple 10-meter resolution grids together. These are from Natalie, actually, who was our data manager on board for American Samoa. And yeah, we ended up providing a couple really interesting updated maps of Waiulu at a high resolution, and also do some really interesting water column sampling with the Mesobot there. So it ended up being successful after a couple of engineering hiccups. A lot of the workup that we did leading up to this ended up paying off, and we were pretty happy with the capabilities of the system. So yeah, that just about wraps up what I was going to cover today, this operation in American Samoa. And now Val is going to talk to you guys a little bit about another operation we underwent with 2 other DriX vehicles. Thanks, Avery.
Does anybody want to ask Avery questions while I queue up the next presentation?
Yeah, what were the sea conditions on the second more successful?
The seas had come down a little bit, but we were still seeing, I don't know what our significant wave height was, but it was larger seas than we had anticipated and pretty harrowing.
Up to 3 meters, like that became like we had to set a new limit for what our comfort zone was, because it had been at 2 meters, and we'd have never left the harbor. Like it was, and so we were out in 3 meters significant wave height, and when the boat would stop every once in a while, which it does from time to time when you plan the next thing that you're gonna do, like all boats do, it would turn sideways into the waves and then rock back and forth, and you just said a prayer and hope that nothing rattled loose. Like
You must burn a lot more fuel too.
it did, and that made it really challenging to manage the endurance of the vehicle over 100 nautical miles. If you make a mistake 100 nautical miles away, there's not a lot of forgiveness. Yeah, for sure. Yeah, like we've talked about this a little bit, and you can do these operations. You have to be super careful. There's a question. I mean, like the question is like, can you do them? Yes. Should you do them? It may be a different question. Because, you know, we've never done it without Nautilus there to be able to at least put us on a tow and bring us back. So of course, doing it with one vehicle wasn't enough. We got back, and like a month later, we went to sea to do this again with 2 vehicles, this time in collaboration with our friends at NOAA. So this was also funded by the Ocean Exploration Cooperative Institute, with a bunch of other people helping to underwrite it. BOEM actually paid for the bulk of this. But there was donations in kind from OMAO and Office of Coast Survey. They did all the data processing and all the watch standing for sonar operations. Deep Sea Coral Research Program underwrote a little bit. And then I have Linker and Exail here. They're both, so Exail is the company that makes the DriX, and Linker is a contracting company and both of them, we hired contractors from them for support, but they were so interested in this operation, they actually donated additional people to help with the effort on their own dime for the travel and all of that. The purpose of this mission, I mean, the purpose was the mapping mission, and that's what BOEM was interested in, but really the purpose, what we proposed to do, was to identify all the challenges of operating multiple vehicles at once, and to try to fix the ones that we couldn't and document the ones that, fix the ones that we could and document the ones that we couldn't, and work with Exail and other folks to sort out kind of the operational model and all the logistics of that. So this was our operating area, the place in magenta there. This is of course Cape Cod here and CCOM up at the top. And there was a BOEM wind farm lease area that we overlapped with quite a bit for obvious reasons. 40 nautical miles offshore here, almost 90 nautical miles offshore up to CCOM, so we decided it was better to come back to Provincetown for refueling and maintenance. So we put sort of a field support team there. We called it the Rock Light, and then just upstairs here we established the sort of main watchstander station, Rock, upstairs. Avery gave a hint, but it's just a challenge to you totally think about operations differently when you're operating this far offshore, because what KG likes to say, you got to think of the maintenance routine for the boat like you do an airplane, because the cost of something going wrong when it's out there is just so high. So we doubled and triple check everything, and if anything seems like it's out of whack, it gets replaced with something else, just to try to keep the vehicles as reliable as we possibly can. You can't read this slide. It's just my way of getting my head around the whole operation, and I'll walk you through it real briefly, and then we'll talk about some of the details. So our mission was 28 days long, 21 days long, bracketed by a mobilization and demote, which are these purple blocks on the sides. The times that we were weathered out are these green bars. The DriX 12 got fouled. I'll tell you that sea story in just a little bit. That's the red bar there. The times that we were at sea are the blue bars at the top, and the green ones we were in port. And then the red, of course, is when we were fouled. I laid out all of the weather forecasts there so that I could look at all the things that happened and try to have a big infographic of the context of all of that. So let me talk about our preparations. One of the things that we did was to brief the Coast Guard on these operations, and this was the brief that we gave in a nutshell. We told them who we were, and we told them about some of the stuff that we've done deploying off of other boats, so they didn't think it was our first rodeo. And we told them about the project and where we were gonna go and when, and we told them all about the DriX, the sensors it has on it, its ability to avoid things that it senses right in front of it, what our watch station would look like, and our watch standing routine for all of that, and what we were gonna do if there was a failure. We had a plan, we wanted them to know what that was. And they were super thankful and had some feedback for us that I'll go through here a little bit. I think they often don't get briefs like that that are as detailed about an operation, and they were like, this is great, this is really helpful, it's helpful for us to see all of that. They asked, interestingly, about the DriX and its survivability at sea, and whether or not it had been certified by a certification body like Bureau Veritas maybe, or what's the Norwegian one? DNV, thank you. And DriX has actually been certified by Bureau Veritas, and that gave the Coast Guard a sense that it wasn't a complete mystery what the engineering survivability of the boat was going to be. They said, okay, well, this is kind of a NOAA operation, so you don't really have to follow any of our rules. But these are the recommendations that we would give a commercial operator. And NOAA's current policy is different from Coast Guard sector to Coast Guard sector all around the country. So I included some of the recommendations here for other people who are doing these operations to see what we were required to do, because it's different everywhere else. Part of the feedback they gave in their letter, they described our USV as completely autonomous, and like, we never called it completely autonomous, and I kind of, like, we had people in the seat standing watch over it continuously 24/7, but in their formal letter, they described it that way nonetheless. They told us that our boat didn't meet COLREGs, and I was like, well, it's true that we don't, like, there's one provision of COLREGs for sure that I know that we don't meet, but we met COLREGs every other way by having a person, so maybe I should explain what COLREGs is. So COLREGs are the guidance that by international treaty that's given to mariners to prevent collisions at sea. It's like how mariners are supposed to operate when they come in a meeting situation. And if you're a robot boat, you're supposed to have all of that programmed in place. But they said we didn't meet the strict intent of COLREGs, even though we had somebody monitoring the boat 24/7. And I asked specifically about that, and they said, well, Rule 5, by look out by sight and sound by a human. You don't have a human on the boat, so we're never going to meet that one because we're not going to have a human on the boat. And actually, we don't actually have a way to monitor by sound, a research project that we're going to undertake. But they also said that that's just kind of the blanket policy that they have for all robot boat operations, which is what it is, I guess. For normal robot boat operations, they would have us have a quick yellow flashing light on the boat. We didn't actually do that, but they wanted us to escort the vehicle initially as far as 12 nautical miles offshore, which would have been total pain to have to escort the boat out that far. But as we talked to them more and they learned about the operation that we were doing and the capabilities of the boat, they actually sort of backtracked and they said, well, you don't have to really escort it that far. And in the end, we escorted it out maybe a couple of kilometers out of the harbor and then back in on every go. They wanted us to keep them informed and they wanted us to tell them if anything went wrong. And we sent them project updates every 2 or 3 days during the operation. We reviewed all of the things that we could find about collisions and incidents with ASVs or robot boats at sea before doing this operation. We wanted to know and learn as much as we could from that. We created a communications plan between NOAA and UNH so that we had like a plan of what to say and what to do if something went wrong. We issued a local notice to mariners and notification of field work with the local harbor masters that notably did not put any restrictions on fishermen because Saildrone got in a lot of trouble for doing that in the previous operations. We tried to learn from them. We set up the remote operating center upstairs. It's not a trivial thing to do this, to support 2 boats to have enough desktop real estate that you can see all of the things that you want to see just at a glance and not have to dig down through multiple menus and windows. To think about the details, like having a desk phone there so that you can call the rock and you're not trying to call somebody's personal mobile phone who's not on watch and not there. Having backup capability, thankfully the building has a UPS and a generator backup. We put a Starlink on the roof because of course the university's internet service went out in the middle of operations, and we had to have that staged already. And then like a push-to-talk mic on the desk, because as Avery talked about, we've installed VHF radios. We need to be able to communicate with other boats, but we also use that to communicate with other folks in the operation. And then the watch station set up off to the side, usually manned by, or crewed rather, by just one watchstander, but you can see the two data acquisition systems for the two sonars, one on each boat. And these are just, well, they're not just remote desktop sessions, they are remote desktop sessions into the boat, but with some special sauce that is too detailed for me to talk about, that allowed us to have multiple connections in at once. We also set up the field station down in Provincetown. We took a bunch of CAN dock down there so that you can kind of assemble, piece together however you want to provide docking stations, and our rib down to support the boats coming in and out of the harbor, and a small watch station for folks down there to help monitor. And then a big van full of spares and to replace everything that might go wrong. And then, yeah, so the hardest part about this whole thing is like how you communicate with everybody all the time. And like cell phones are not enough and not good for an operational watch. And sorting this out with people from different organizations is pretty tough. It seems like it should be easy, right? Because there's all these technologies that you can bring to bear to this. But when you start mixing people from within an organization to with outside an organization, like Teams at the university doesn't handle chat very well when you're sharing files with people outside the organization, or Zoom you can't do file transfer for. Google is the platform of choice for NOAA, which is great, and we could have used that, except if you add somebody into a Google chat, for NOAA at least, who's not part of the NOAA organization, you only get 24 hours of history of that, and that didn't seem right. So sorting the details out of all of this and all the authentication was like one of the hardest things about this whole project, honestly. We purchased a piece of software called V-Link that is used aboard, this is the control van aboard the Nautilus, the ship that Avery showed you. It's used aboard the Nautilus in conjunction with like physical consoles with buttons to provide audio party line between operators on the ship who are operating, robot boats and or underwater robotic vehicles. And the software is designed for like control stations for like television broadcast or for like military operations. So we hosted this on a server at CCOM with some help from the IT team. We set up two party lines, one for DriX pilots and one for DriX guests. And with that setup, you could open up a browser and immediately communicate with the watchstanders upstairs, the pilots who are monitoring that 24/7. So you could do it from your phone if you were standing on the pier. You could do it from your phone if you were out on the boat. You could do it from home in the middle of the night if you need to provide support for the team out there. It has some hiccups, but it really helped to bring everybody together and communicating well. Before we got underway, we did a patch test. This is just like a pretty shot of multi-beam data. And we did a reference surface for both of the vehicles to make sure that they were saying the same thing before we went. This co-survey helped us with all of this. We found that under certain conditions, so we asked NOAA to get Marine Star subscriptions, corrections to their GPS on board, because we were so far offshore. And we found that the fins, which is the inertial navigation system on the DriX, would often reject those GPS inputs when there was a cycle slip. And the outfall of that is that the fins would eventually stop navigating. And when it stopped navigating, then you have no heading reference either. And the only thing you can do is physically reset it and do figure eights. And when that happens, it's a royal pain and certainly dangerous and not good for mapping either. So this was a challenge, and we worked around it while we were out there. We still don't fully understand one of the symptoms of the problem is the uncertainty of the GPS when it's getting those fixes is constant. It's not changing. And of course, the GPS receiver should be outputting something that's proportional to what it thinks the uncertainty is. And because it's so low, when there's a big step in the vertical position from a cycle slip, the INS is rejecting it. It's too far away from the solution. So that's something we have to investigate more. Avery already talked about fuel consumption stuff, so I'll skip that, other than to say that interesting, NOAA's 2 DriX vehicles have like markedly different endurance. So much so that over a full deployment, it's about a 12-hour difference in their operations. DriX 23 happens to be better and has a smaller prop, which is, I think, curious. This was our watch stander, like our entire team. So Larry was providing benevolent leadership. The folks in green there were sort of our sort of supervisory master watch standers. The ones in blue, these were the watch standers that had stood watch on DriX or other USVs and probably had well over 100 hours of experience. But you notice there's not a lot of them. All of the folks in pink had like some training on DriX vehicles, but never really stood a watch before. So these were not people that were likely to stand a lot of watches by themselves. The folks in yellow were standing watches for sonar and data acquisition. The folks in orange were doing data processing, actually at the Pacific Hydrographic Branch in Washington. And then the folks in kind of, what color is that? Green, blue, teal, are contractors that were providing both technical and software support during the operation. Our watch standing started like this, with a 3-section watch every 8 hours, and surveyors doing what surveyors do. Those unqualified, kind of under instruction folks helping out, but really the intent was to try to minimize the watch team as much as possible, and so that pilot was going to manage both vehicles at the same time. And then we would have a DriX master, kind of supervisory person providing support for these guys. But we found really early on that this just didn't work. It just wasn't safe enough. There were too many things for a pilot to manage to manage both vehicles safely. So we made like a pivot, and we field promoted the junior pilots to full pilot status, and so they got a DriX. The pilot got a DriX, and we added a supervisory person excuse me, on top. So this is kind of what it looked like. Excuse me. With a pilot managing one vehicle, a junior pilot managing the other, and the DriX sort of master supervisor, myself or Josh or Tyler, looking over their shoulders, keeping them out of trouble, thinking about long-term endurance and planning, interacting with other people outside the room, helping to troubleshoot things that went wrong. And the pilots sort of universally said in our debrief of all of this that the DriX supervisor person there was like really critical and somebody that they wanted in the room most of the time, because there was a lot of things that could go wrong, and it was really helpful to have that support. I'll just mention briefly, we didn't start this way, but we staggered our watch rotation so that those two pilots were changing watch 4 hours different from, shifted. And that turned out to be a super useful thing to do to maintain continuity of information across the watch turnover. This was just like my slide for the Provincetown field team. So finally we get underway on October 7th. So it was rainy and you don't see 2 meter seas here in the harbor, but out at sea it was 2 meter seas. 2 meter seas in the Gulf of Maine is every bit as bad as 3 meter seas in the Western Pacific. Like the wavelength is shorter, and you could see the boat struggling in that kind of weather. In the first 48 hours, I don't think I slept at all. in part getting all of the watch standers sort of comfortable, but also the DriX 12 Starlink continuously was dropping out every 10 minutes, probably 2 or 3 times for durations of 10 to 40 seconds or so. It would turn out that we would get, let me back up. It would turn out that we have a good story about Skylar. It would turn out that DriX 12 was an early version of the Starlink dish that only had a single IMU and couldn't track the satellites very well. DriX 23, who had almost no dropouts during that time, had a newer version of the Starlink dish. So we're in the process of updating all of the Starlink dishes that CCOM has, but we returned DriX 12 to port to swap out that Starlink dish for a newer one. And when we did, we learned the hard way. Well, we knew this was going to be a problem already. We just couldn't convince Exail. So Skylar, many of you guys have met Skylar. He's one of our engineers who is kind of new and sits upstairs. And I'm sort of making fun of him here, but the guys were out about to swap the Starlink antenna, and Skylar was up at the operator station looking at the display, and they called him on the radio and said, "Skylar, can you secure the Starlink?" And he said, "Sure." And so he goes to secure the Starlink, but like, which DriX is this? The display is identical for both vehicles, and he secures the Starlink on the one that's still at sea. And so there's like no way to know. And so we had software support guys from Exail in the room, and Loic is one of them, and he came over and was watching what was going on. And I was like, Loic, we can turn this back on via Iridium, right? Like that's a thing you should be able to, we actually asked for that as a feature upgrade, and we tried it and it wouldn't turn back on. And it turned out, you can't see this very well, but these are all the circuit breakers on the DriX, and these are a special kind of like digital on-off that actuate different kind of relay on the DriX. And they implemented that Iridium turn on and off feature for everything except for this. And that's the Starlink right there. But it worked on the boat. It just didn't work in the operator's thing. And I was like, Loic, could you fake that message? Could you like code something up to pretend that that was sent, the command was sent, and he like sat down on his computer and worked away and hit a button and it came back on, and DriX 23 was back, and that's Loic. Totally worth having him there. So then we finally convinced Exail to change the display to put those bars across the top that don't change when you scroll, that are color-coded, because you would be surprised when you're quickly going through menus and trying to manage 2 vehicles, and it's stressful how easy it is to not see the numbers, the stuff that's right in front of you, to try to give people a hint on the display. I think I'll skip that for the sake of time. Okay, we had a downtime, a couple of days of downtime because of weather. So we got all of our pilots together in a room, and we asked them, like, what were the things about operations that made it really limiting and difficult to do multiple vehicle operations with one pilot. And we started off that discussion by talking about all the critical things that they're constantly scanning when they're on watch to keep things safe. And these were all the things that they came up with: the radar, the engineering data that's coming in, the health of the communications, the obstacle avoidance system. And then we asked them what things about these made it difficult to keep things safe. And they came up with a giant list that includes everything from, like, to turn on the radar and display data takes like 11 clicks of the button. And that doesn't seem like it should be a big deal, but that combined with everything else, designing a user interface for multiple vehicles requires some real thought into human factors and all the things that build up, like cumulatively build up in your cognitive loading. Some of it, like, there's no audible alarm when the obstacle avoidance system triggers and the vehicle goes off course, which may not be a big deal if you're looking at it all the time, but when you have 2 vehicles and you're focused on one, it's nice to know that the other one. So we wrote a paper about this, a report. It had something like 47 items in it. we submitted all of those as feature requests to Exail to try to improve. I'll skip this, I think. I'll just say that the software team, the two guys that were there, they did a bunch of updates to the system from direct feedback from the operators. In my opinion, this is like the fastest way to get technical development, like new technology that's practical and useful into a released set of software for a piece of gear, is having the development team on site, watching what's going on, talking with operators about stuff. And they fixed all kinds of things that were really helpful. And I detailed these for the other presentation, but I'll skip them for now. This is like a beauty picture of sonar data. This is not as interesting as the next one. This is the backscatter off the coast. These are iceberg scours in like 200 meters of water, and some of these are like sort of 30, 40 meters across and 5 or 6 meters deep. Like, it's fascinating, I think. Okay, I'll tell you real quick my story about DriX 12. This was the view for the pilot on Friday at 5 p.m. on October 11th. And then a minute later, he got an engine stopped warning. No idea why. DriX 12 is like 45 nautical miles offshore. The first thing you look at is all the parameters for the engine itself. The most important ones, the oil pressure and the coolant temperature, those read 0. Why do they read 0? Because you don't get that data when the engine's not running, and there's no history in this display, which is unfortunate. So you have no idea what they are. But we knew that, and so we plot those data fields in real time as a time series so that we can see. And there's no indication in any of this why the engine stopped. The engine just stopped, and all of these parameters just go to 0. We looked in all the cameras. We looked in the camera inside the engine room. We couldn't see anything amiss. And so at this point, rolled out the procedure. We had a plan for this. And as Avery mentioned, 6 months before, we all had gotten together in a room and talked about this scenario. And we laid out exactly what we thought we should do. And we argued about it for like a day and a half. And one of the things that fell out of this is that you don't want to try to continuously restart the engine, because if you do, you deplete all of your battery reserves. You have no ability to transmit on AIS, to have your navigation lights lit at night. It makes it much, much more difficult to find a vehicle if you have to. So we tried to restart the engine, I think 3 times, and after that, we was like, okay, we have to do a dead boat recovery. To make a long story short, 48 hours later, this was the view of the DriX with ghost fishing gear all wrapped through the screw, totally bound, which we couldn't see in any of the cameras. We had some help from NOAA ship Hassler to put the vehicle on a tow, but we would eventually send out our own team to go out and recover it. There were a whole slew of lessons learned. The first 2 folks that we tried to get to go out, that we had contracted one of them in advance, actually we contracted both of them in advance, refused to go. One of them probably because it was Friday night at 6 o'clock when we called him, and he'd probably had a few beers by then. But it was clear that you got to have a deep bench for those kinds of recoveries. And a whole slew of other things. Like, this was the weather forecast. The event happened over here. There was a stretch of really bad weather where we probably wouldn't have gone out. And then a window, which we did go out to recover the vehicle. But had we not gotten the vehicle then, we had like 3 or 4 days of bad weather that it would have just been adrift. And it might have drifted so far that we couldn't have gone out in a boat this size safely to go and get it. So those are other things that give us pause for thought, for sure. And then things like, if you have to do a recovery that's more than 25 nautical miles out and you can only tow at 5 or 6 knots, you're almost certainly going to do part of that recovery at night. And a lot of people don't feel comfortable sending a boat this size 50 nautical miles offshore with a crew on at night. There's things that you have to remember. That's what all of that mess looked like up close. When the whole mission was over, we stopped 2 days early because of weather in the last 2 days. For people who think in these kinds of numbers, we covered about 420 square nautical miles and 2,700 linear nautical miles for all the cross lines that we started with and the mapping that we did. There's like 504 hours in that 21 days, and we were operational and at sea about half of that for each vehicle. And most of that downtime was weather. Very little of it was maintenance related. 190 hours we were weathered out. So lots of things to learn, lots of things to think about for future operations, and lots of thanks for all the people who supported, particularly this crew, fantastic crew of young women who you will see in this field, I think, a lot in the future. They were great. The folks from NOAA, the NOAA officers, and of course our grad students, and Acacia Kedor from the National Naval Oceanographic Office was really terrific. So thanks for your attention. I apologize, it's pretty long. I'm happy to take questions, but I totally understand it. It's Friday afternoon, guys. I'm out of here. Yes, sir.
For lessons learned, was the weather support from the National Weather Service adequate, or what was missing for your October?
So we did have daily reports. When we were in Samoa, we had daily reports from the National Weather Service, and we had some reporting from the National Weather Service for here, but we used primarily windy, and largely just because the display of information is just so much more intuitive in windy than it is in the National Weather Service sort of standard plots without color and wind barbs and all of that kind of stuff. Yeah.
Talk about the drift model.
Yeah, so we didn't talk about that, and I do have a slide about that, but I didn't leave it in this presentation. The Viz Lab very helpfully made a visualization with some help from John of the surface current from the Gulf of Maine operational forecast system. They also did it for us in the South Pacific from the Stoff's 3D model, and then created a tool for us so that if your vehicle's lost, you can click in there and stick a time in, and it will show you where it thinks the vehicle is going to go just based on surface currents. And its predicted path actually looks just like, but slightly stretched for DriX 12's event for 48 hours. But something that we've been talking about publishing a paper about, because that kind of a data point for that kind of thing is pretty hard to come by for drift models for that kind of, for vessels. Yeah.
So with these over the horizon operations and DriX being so off coast, if the seas were to change rapidly, what are the chances that DriX could slip?
I would say almost impossible. You can't see it here, but there's a gondola underneath with, I forget the weight of the gondola, but it's mostly full of lead.
Okay.
So it's like a sailboat with a lead keel, and it makes it really stable. There are weird conditions where it will roll a fair amount, and it's conceivable that you could be in steep enough waves that it would roll and it would take a wave over the Starlink antenna or maybe even over the sail in really bad weather, and that would probably cleave off all the antennas. But I think the vehicle would survive through all of that. Yeah. Yes, sir.
The ropes and the buoys you followed, they drifting, or what was the source of them?
Yeah, that's my best guess. There was a log wrapped up in it. Some of it was line, some of it was net. I think somebody probably got their fishing gear caught in a log and just cut it free. Yeah, and I think it's pretty common in the Gulf of Maine, actually, unfortunately. Anything else? Yes, sir.
So just a general thing, would you be considering running an over-the-horizon operation with even less support on site, or within 100 nautical miles? So your main center is in East Coast and you're operating out of American Samoa with only 1 or 2 people out there. Would you ever move to that kind of model, or do you still want part of the team nearby for maintenance and things like that?
I guess there's 2 parts to my thoughts about the answer to that question. So when we, in our American Samoa operation, the reason we had 2 operator stations, one here and one there, is we just had no idea what the internet service was going to be like in Samoa.
Yep. And
we didn't want to have the boat drifting. So we had one person on watch in each station 24/7. But to get maybe better to your question, like, I think it just depends on like where you want to map and the practicality of where you need to go to refuel when you need to refuel. And if that's, you can put the operator center anywhere, and I think that works as long as, you know, you can maintain a 24-hour watch. But the one thing you always have to have locals, whoever's gonna refuel the thing when you need to.
Another thing, is at-sea refueling at all a possibility?
That's a great question. So there's like a port on the back, like this little nipple right here is a refueling port, and we've actually never done it. Other folks have done it. If the seas are calm enough, you could totally send a boat out while the DriX is surveying, and then stop the DriX, and they pull up alongside and refuel them, and then head home. It's a.
Tell them about the original DDS design.
Yeah. So the docking system that the DriX pulls into when you're going to pull it aboard the ship, the concept of that is that DDS would both refuel the vehicle and change the oil while it was docked in there. Because it turns out, changing the oil turns out to be one of the big constraints to operations. This boat, you do probably 3 deployments, and then at least by the engine manual, you should change the oil, sort of 3-day deployments. So that becomes a constraint, and with the bigger vehicles, Exail makes 2 larger vehicles that endurance is longer, you end up changing the oil a lot. Yeah, it's a thing. Yes, sir.
I'm just curious, with the bigger DriX vehicle, withstand like the weather more than the DriX 12 and 23?
It's a good question.
Can you repeat the question?
Yeah, I think, so I understood right, you're asking if whether or not the bigger DriX vehicles would have a larger weather window. I think, so there's 2 vehicles that Exail makes. One is just a meter longer than this vehicle, so not much bigger, but has twice the fuel capacity. That one they call H9. And then the other one is H16, so a 16-meter long vehicle, much bigger than this. And I would have to think that would be much more survivable in rough seas. Just the sheer size of it, all the antennas are, in fact, the antennas on that vehicle are all enclosed inside the sail to protect them. So that one should be really survivable, I think.
So what about the degradation of the mapping?
John Hughes Clark has shown, like, in really rough seas, like bubbles entrained in the water column down like 10 meters or something crazy like that, and including, so there's some limit to what you can practically do with any sonar. Even in the 3-meter seas, because the sonar is 2 meters below the surface, I'm not sure that we saw any indication of degradation of data. It might have brought the swath in a little bit, because Kongsberg systems will sort of do that all by themselves when they're having a difficult time with signal to noise on the outside. But there weren't like blowouts that you sometimes see from like bubble sweep down from underneath. We didn't see anything like that.
Yeah, a lot of the uncomfortable times that we had in larger sea states is really when you're going slow or when you're not moving, is when the vehicle becomes really unstable. But when you're underway, due to the design of the hull, it's fairly stable, and depending on the setup that you have and the angle that you have to the seas, it's not horrible.
But it's also fair to say you've experienced some pretty awful sea states, and it has survived. So we fortunately, blessedly, haven't reached the limit of survivability in all the conditions.
That's true, but we have like just a couple data points, and we've seen failures of other things in much more benign conditions that, like, Ethernet connectors aren't meant to be wiggled,
Yeah.
and you can't have a wire that's loose anywhere in the boat.
Can I add to this?
Yeah, please.
One thing we did notice was the heading control on the DriX sometimes was too aggressive with the sea state. So while it would keep its line, you'd see the lines kind of doing this, just chopping around a lot because it was because of the control.
But that's an active thing. It's
an active
doing
control.
it's not the dynamic of the vessel.
Yeah,
But
it's
so
the
it
active
should be
control.
something, we talked about that
Yeah.
should be.
We talked to them the first time, and they gave us like a coarse, medium, and fine heading control, and they wouldn't give us like a knob that we could dial ourselves to find the right answer. And I really want the knob that we can just play with, because the conditions are never coarse, medium, or fine, it seems. There's another quirk with that problem too, and I think it has to do with the way the 2040 steers in 200 kilohertz mode. It has two sectors, and in our data, there's some big gaps at nadir because the yaw steering sort of jumps and in a way that leaves a gap when it's steering hard like that and doesn't sort of smoothly adjust back and forth. It's something that we talked with Kongsberg a little bit about, and there's that knob for how it sorts out your mean heading, which we didn't dial because we didn't recognize it when we were deploying.
Well, we did play around with all of them, but it was hard to get a constant, good result.
Yeah,
You kind of had to go as
very hard. Anything else? Well, thanks everybody. Happy Friday.